Good afternoon. I'm Sriram from NIST, and this will be a joint presentation with Mehmet. We've been working with him closely last couple of years. It's also joint work with my colleagues from NIST. Doug Montgomery and Oliver Borchardt are here. I would also like to acknowledge Randy Bush. He has had some inputs in the past on some of the convergence modeling work that you will see later in this talk. The talk is about BGP SEC performance, particularly about optimization algorithms and efficient software architecture that lead to high performance BGP SEC. I will be dividing up, we'll be sharing the talk, as I said, and it'll be in three parts. Initially, I'll spend some time introducing BGP SEC, followed by that Mehmet will talk about the optimization algorithms and the software architecture. And followed by that, I'll come back and talk about convergence time. So we have known about BGP vulnerabilities for a long time. Prefix hijacks, prefix squatting, AS path modification, man-in-the-middle attacks, Capillo-Pilsov type of attacks, and forged origin attacks as well, and route leaks. So IETF, there's been very active work in the IETF for the past several years to address these issues. This slide says objectives of the CIDR security solution. In fact, I will be using this slide to talk about the significant things that have already been accomplished in CIDR. To start, the origin validation work has already resulted in multiple RFCs. In particular, RFC 6811 provides the basic validation algorithm for origin validation. And together with that, RFC 7115 provides best common practices for origin validation. And then we have the BGP SEC draft, which has recently been approved by the IETF to become a proposed standard. So you will hopefully see the RFC come out in the next 2 or 3 months. There is work in the CIDR working group also related to protection from withdrawal suppression and malicious replay attacks. And in the references, we have included a draft which talks about the solution for the replay attacks. The BGP SEC protocol also accommodates special cases. Those include transparent route servers, for example, at internet exchange points. And also, when you have a confederation, the confederation must be visible outside as a single public AS. External to the confederation, it should be visible as a single public AS. So those things are accommodated in the BGP SEC specification, as well as multiple other things. Once you look into the draft, you will see. Route leaks detection mitigation work has been in progress in the IDR working group, and there are a couple of drafts there that are under consideration. The key elements of the solution that has been developed for origin validation and BGP SEC path validation, I'll try to briefly talk about that here. There is hierarchical certificate chain for resource allocations for the IP address prefixes and also for autonomous systems. So once an IP prefix holder has the certificate, they can use the RPKI repository, and they can place a route origin authorization, a ROA, in the RPKI repository. The ROA authorizes an AS to propagate one or multiple prefixes. So with the help of the ROA, origin validation can be done in the routers. And I will talk about the next 3 bullets, perhaps with the help of this diagram in the next slide. So this shows us the basic principles of BGP-SEC path signing. As the update propagates from the left to the right through multiple ASs, each AS assigns the update to the subsequent AS, and the signature covers the prefix and the AS path, as well as any previous signatures in the update, if there are any. So by the time this update makes its way to AS5 at the right-hand end, AS5 has 4 signatures to verify in order to validate the path. And it can also look up the ROA information to validate the origin. So it can do both origin validation and path validation. As like I said, the signatures cover the prefix and the AS path. So the AS path is protected, the origination is protected. The signature is also addressed to the peer. So the signature includes, in the data that is hashed and signed over, it includes the target AS or the next hop AS. However, the next hop AS is not carried in the BGP-SEC update. So once you have this path validation in place, essentially you have a complete path protection. There is a guarantee for AS5, for example. In this example, there's a guarantee for AS5 that the BGP-SEC update has indeed traversed the ASs that are shown in the AS path. So that's the guarantee that BGP-SEC offers. By doing this, you are preventing any path modification attacks, obviously. You are also preventing any prefix modification. If somebody replaces a prefix with a sub-prefix, that would also make the update invalid. And also any such thing as a forged, somebody may try to take advantage of the ROA and insert a forged origin, in which case whoever is forging the origin would not have a signature from the origin, and therefore even forged origin attacks are detected by this scheme. Now, what is the BGP-SEC protocol introduces a new attribute that we call the BGP-SEC path attribute. The path attribute consists of a secure path, which includes the AS numbers in the path, and together with that, it also includes the P count or the prepend count for each AS. And there is also a flag field associated with each AS. By using the flag, by setting the flag, the AS indicates that it's part of a confederation, and that information is used as the update egresses from the confederation. That information is used to detect that the set of signatures were inside a confederation, and that set of signatures is removed. And when the update progresses out of the confederation, the signatures in the confederation not all of them are included. Only the confederation's public AS signature would be included. And the lower part of this picture is signature blocks. The signature block includes several signature elements, and each signature corresponds to one AS. So there's one signature per unique AS in the AS path. So that is a very brief introduction to BGP-SEC. Obviously, there would be questions about the performance of it, the CPU workload, etc. So Mehmet will now take you into the efficient software architecture and optimization algorithms that contribute towards high-performance BGP-SEC.
Thanks, Sridhar. So anytime we take a protocol such as BGP and we add security to the protocol, there's always a question of, well, am I going to be able to converge? Is this going to be real time? Or what is the compute and other requirements on the new security elements? So let's take a first look at what those compute resource estimations could be based on certain assumptions that we made. The first number is 600 80K prefixes, assuming about 4 hops per path. And that's a typical assumption based on data collected. And then we're also assuming that there are about 55,000 ASs out there, right? And then start multiplying the numbers, and then there's, the space kind of grows. Now, the assumption is that BGP-SEC will probably grow in islands. There'll be certain islands supporting BGP-SEC, working with BGP, and over time, it will grow to be mostly BGP-SEC. Now, a typical BGP-SEC router is going to verify on average 4 signatures, 1 per hop, if you will, and that's per algorithm supported, per update. And then once the validation is done, let's say, if it's propagating that particular path, it will sign it. And it will sign it, it will be a new signature, and it will be per update, per algorithm. The algorithm that we're talking about here is, if you remember in the previous slide, there was an algorithm ID. This is the particular algorithm based on the protocol that's being used to sign the paths. Right now, ECDSA P256 is the algorithm of choice, and that's in the RFC of the algorithms. So that's what we're basing these discussions on. And then real quickly, if you look at per update signing, each AS will actually need a private key to be able to sign that particular path. These keys aren't really that large. However, they need to be, their confidentiality and integrity must be maintained, so the system should be able to do that. Now, for the validation, though, for each hop, we need a public key of the AS that the particular path, let's say, was signed with. So if you're assuming 4 hops, that will be 4 different public keys. The public keys are a little bit larger than private keys, but still, the size isn't a problem. It's the number of potential public keys that we could have that, full propagation of BGP-SEC. And we'll talk a little bit about that as well. So real quick, the ECDSA signature operation is shown in this diagram. The top one is, let's say, for algorithm 1, P256. The bottom one is for, let's say, another algorithm of choice, maybe P384. And these signatures will be calculated, generated, and they will be put in the signature block. And they can actually be done in parallel, or they can be done in sequence. The validation gets a little bit more involved because, remember, we have multiple segments in a path. So, we need to validate each one of those, right? And all of those hops, or all of those paths, must be valid for the segments must be valid for the whole path to be valid. So the top one shows it if you had 1 algorithm, and the bottom one, adding another algorithm. And if we were supporting 2 algorithms, we would have to do this process for each algorithm. For those of you who have been involved with ECDSA signatures or most signature generation schemes, there's a lot of computation that goes into those particular operations. So what we wanted to do was we wanted to evaluate a large number of signatures being generated, and we're considering millions of signatures generated, millions of signatures validated. And in most applications, you don't see that. If we're signing a document, you'll sign so many documents, you will send them over. But in this particular case, there's real-time requirements, convergence requirements. So when we started looking at optimizations, we started at the top level, and those are system-level optimizations. So as an example, given a router plane, what kind of resources do we have? Do we have multiple cores on a router plane engine, right? So can we do certain operations asynchronously? Can we do the verification for the path in parallel, because each hop can be actually validated on its own? And then also looking at the large number of potential public keys, what memory models or other models or even compute models do we need to speed that up? And then we looked into algorithmic optimizations, and examples are, going back. So when you think about from a BGP-sec perspective, if you're validating a long path, right, and it has multiple hops in it, if any of those hops are invalid, well, the whole path is going to be invalid. So if we found, let's say, the second or the third element in that path is invalid, we really don't need to go look at it anymore. We can just claim that the whole path is invalid and terminate early. For ECDSA sign operation, and we'll show an example of that, we could do pre-calculations. Beyond that, we start getting into the math side of things. The group level optimizations will be within the ECC groups that we're looking at with ECDSA operations. And then as we get into the field level optimizations, that's now another layer of getting deeper into the math, looking into the special forms of domain parameters and looking into multi-scalar operations and reducing those and the time taken by them. So let me show a quick example of an algorithmic optimization. So the ECDSA sign operation is shown here. And if you notice, that top part here has no dependency on the message that's being signed. And the message in this particular case is the path that we're going to sign. And maybe that path is about 1,000 bytes or whatever it might be. But the actual work of generating the approved random numbers and doing the point multiplication is actually the heavy side of the calculation. Well, in this particular case, since it does not depend on the path that we're going to be signing, we could actually do this at any time we want. We could do it on an asynchronous core. We could do this ahead of time, and if we knew how to actually maintain that, then we can get substantial benefits out of this. Now, you have to be careful. These have to be done in approved forms, and actually ECDSA is one of the signatures that you can go find this documentation on, and pre-calculations are explained. I should also mention that we put references in the back of the presentation. We actually have a full paper on the optimizations that you can go read details on. Okay, I won't spend that much time on this one. There's a lot of information here, but really what is just showing this as an example where we start looking at lower levels, and a traditional point multiplication will take about 128 point additions and 256 point doubles. And remember that for P256, this is a 32-byte multi-precision integer, right? So these are not just adding 264-bit numbers or 32-bit numbers. These things get quite involved pretty quick. And also, they're not side channel attack resistant. So we can take the algorithm, we can break it down to pre-calculations and evaluation stage. And effectively, we can reduce the evaluation time to only 64 point additions. And that is a tremendous improvement over state of the art. Let me show you, though, what these numbers kind of mean at realistic levels, right? So the chart actually shows numbers for P256, which is the algorithm of choice for BGP-sec today, and we put its bigger brother P384 to kind of show a reference. P256 is approved for many more years. I think it's good up to 2030. But we also wanted to show an upgrade path if an upgrade was necessary. Some of the numbers to remember here, doing the sign operations, if a hash is provided or not, typically over 40,000 signature operations a second on a single core. And this is with a commodity CPU. And then the verify operations are around 30,000. And how do those compare to, let's say, the state of art or what we have seen? So in this chart, we took the latest version of OpenSSL, which is an open source tool that provides a lot of the crypto low-level functions as well as obviously SSL and TLS, right? So the red marks are what OpenSSL is running on this particular system. Again, these are all single core, and this is what we've been running with the optimization. So this is provided to show that there are optimizations available there. These things can be optimized and actually run to support real-time operations. And then one thing to mention, up to this point, we actually talked about the specific ECDSA operations, sign and verify, because this is where most of the compute time is really going to. But do remember, as we start actually looking at it at BGP-sec level, right, signing a path involves other operations as well. You have to assemble the particular path that you're going to be taking a hash of, and then you're going to sign over it. Then you're going to encode it and put it on the wire, right? And we have done repeated tests with large data sets, and we can still maintain over 40,000 signatures per second, including all of the other elements, and then over 20,000 with P384. Another example is the path verify. Remember, in this particular case, a path actually contains potentially multiple hops. So we need to marshal that data together, figure out what we are going to be validating. So each hop actually has to be dealt with independently, right? So we're going to take each hop, we're going to assemble that data, we're going to hash it, and then we're going to go validate that particular signature. So in this particular case, what we're showing is this is a single core. If you remember, the ECDSA operation by itself was about 30,000. When we add all of these other elements brought in, we're about 24.6 K, which is pretty respectable. And then we also showed another example here. This is actually a 4-core system. And you can see if we're actually using 4 cores, we're about 78,000 BGP-sec verify operations, which is actually pretty decent. And we have tested this all the way up to 24 cores. I'm not sure of any routing engines with that many cores, but there is actually a current routing engine that uses 6-core Intel Xeon CPUs, and then software-based network designs which can run on a server, let's say, and those can typically use more cores. So this is, as BGP-sec adoption grows, multi-threading is a great option to get more throughput. Sure.
Thank you, Mehmet. So we are going to take those numbers that Mehmet has presented for BGP-sec signature verification and also for signing in the context of the BGP-sec protocol. And we are going to fold those numbers into a model for convergence time to estimate convergence time under different scenarios. First of all, we should observe that the BGP-sec update processing is additive to the traditional BGP processing. The traditional BGP processing includes best path selection, implementing peering policies, route filtering, RIB management, etc. The BGP-sec, the additive part of it, as Mehmet has already gone through, it includes parsing the BGP update, data assembly for hashing, fetching public keys, signature verification, and signing to peers. So all these functions is additive to the traditional BGP processing, and we are going to focus on that, the incremental cost, CPU cost due to BGP-sec. This chart shows the update processing speed versus the AS path length. So when you look at a BGP-sec update, it may have different number of ASs in the path. That's what we call the AS path length. The signature, there's only one signature per update. When you send an update from your BGP-sec router to your peer, you add one signature. So that is why the signature pretty much stays constant. It is independent of the AS path length. But the verification speed, updates verified per second, that would be inversely proportional, approximately inversely proportional to the AS path length. The right-hand side of these charts are accurate based on measurements, and as you go to the left, it gets a little bit conservative, but that is okay. So the number of updates that you can verify is 24,000, like Mehmet already mentioned, for a single signature, say a BGP sec update with one signature or one AS hop. And when we have 10 AS hops, it reduces to 2,400, but still not bad, because it would be rare that there would be 10 hop ASs in an AS path. So we'll take these numbers and fold them into convergence models. This one shows that essentially you have 3 adjacent ISPs, which are all doing BGP sec. And the assumption is here is that A and C are 2 very large global ISPs. And we are showing here the customer cone, the depth of the customer cone, and the number of prefixes that originate within the customer cone at various depths. And this is based on real-world measurements for real, very large global ISPs. The ISP on the A on the left has 32,000 prefixes that are originated from its customer cone, and the ISP C on the right has about 30,000. All the prefixes are signed. In other words, we are assuming that all the customer ASs participate in BGP sec. The updates are signed at each layer in the customer cone. And as it gets to the top AS, the ISP's own AS, this is the distribution that we have in terms of the path length, what is shown in these tables. And like we said in the previous slide, the update verification time is a function of the path length. We factor that into this table and calculate the convergence time for R. So if the peering session between A and R resets, how long does it take for R to receive those 32,000 BGP sec updates and compute the validation and achieve reconvergence? The reconvergence time here is on the order of 3 seconds. And the same thing holds if the session between R and C resets. So we are talking about low single-digit seconds convergence time or reconvergence time. That is pretty good. We should mention about stub ASs. Because for BGP sec implementation, it would entail some hardware upgrade. If you have a stub AS, BGP sec allows for simplex BGP sec, what you may call simplex BGP sec. The stub AS can sign its updates to the transit provider, but receive only unsigned updates from the transit provider. By doing that, the stub doesn't have to do any hardware upgrade. It can do simple software upgrade to sign its own prefixes to send to the transit. 84% of ASs in the internet are stubs and 16% are non-stubs. So that's a very large percentage for which the simplex BGP sec can be used and the cost of upgrade can be substantially kept down. Only the non-stubs need to worry about the full BGP sec implementation. This is a model for estimating the CPU cost for validation as well as signing. Once again, we focus on the router R in the middle. It peers with ASA, which has the 32,000 prefix customer cone. R also peers with M, N, and O and does BGP sec peering with them. And R may have multiple other peers, which could be stub and not doing BGP sec. So that doesn't come into the picture here. So if the session between A and R goes down and comes back up, what is the reconvergence time at R? So R has to receive 32,000 BGP sec signed updates, verify all of them, and it has to sign each one of them once towards each of the 3 peers M, N, and O. So that's the kind of processing that's involved, about 30 times, on an average, maybe 30 times 4 120,000 verifications, and 30 times 3 peers on the right, that's 90,000 signatures. So 120,000 verifications and 90,000 signatures. To accomplish all of that processing, R requires about 5.5 seconds. So once again, a single-digit second number, and that is for the incremental CPU cost associated with BGP-sec processing. So we focused on specific scenarios that would be applicable in partial deployment. And just to clarify what partial deployment is, as the BGP-sec adoption starts to grow, ISPs can decide to do BGP-sec themselves and within their customer cone. And so multiple ISs that are adjacent or they form a group, and in that group, they all do BGP-sec. So as long as the update originates from within the set of those adjacent ASs, the prefix, the updates are fully protected with BGP signatures. And when the updates leave the BGP-sec island or this group of adjacent ASs which are doing BGP-sec, when the update leaves the BGP-sec island, then the signatures are dropped and the update is converted to a traditional BGP4 update and sent over outside of this contiguous ASs. So that's how the BGP-sec would work during partial adoption period. And so that's so with that in mind, what we are basically seeing here is that the convergence time contribution due to BGP-sec can remain fairly low in the single digit seconds during the early phases of the deployment. In fact, here we are talking about 90,000 prefixes in 3 ISPs doing BGP-sec. So that's already kind of adolescent phase, if you will. So we have a demonstrated a high-performance implementation of BGP-sec through Mehmet's numbers. And going forward, of course, the BGP workload will increase not only for BGP-sec but also for traditional BGP. IPv4, IPv6 prefixes will continue to grow. That adds more workload, and there would be peering policies, route filtering, etc. All of that workload, the traditional BGP workload would also increase. There will be other factors that we will see that come into play to keep up with the efficiency of BGP as well as BGP convergence. And those could be multi-threading and use of multiple cores in route processors, update processing optimizations besides the optimizations that Mehmet has talked about. And those can include caching the results of verifications and enhanced graceful restart. There is a draft in the IDR on that, and that could help BGP as well as BGP-sec in the future. Thank you. And we have a set of references here which list some of the, there are many RFCs, I should say, contributions from many people. Some of the references are included here. Wes?
Wes George, New Star. I appreciate you continuing to do analysis on what this looks like in terms of the hit to scale and performance. But the thing that I see consistently missing from these bits of information is a comparison to what we have today. How long does it take a router that's not doing all of this, using the exact same CPU, to process the same number of routes with the same number of AS paths, and a reasonable assumption of a typical level of route policy and other things, so that we can see what the actual incremental difference in time is for, because essentially what we're doing here is this ends up being a sales job. You should deploy BGP-sec because it's not actually that computationally intensive, and it's not likely to be the huge hit on processing that we thought it was going to be originally, because things have improved, and we've done a lot of work on optimizations and things like that. That's great. But unless I have something to compare it to with how much better it is or how much worse it is, I still don't actually have a frame of reference for what this would mean in a large-scale network.
Yeah, let me clarify your question. Are you asking about as the number of, I mean, if you consider the full 600 or 650,000 prefixes, every one of them is BGP sec signed, what will be the convergence time?
No. All the analysis you did here had a certain set of assumptions around how many routes you were processing. And you can do simple math on, I can process this many signatures per second, based on this hardware that I've characterized. If I don't have to do any of the crypto, how many routes per second can I process? What is my convergence time?
Oh, just plain BGP, traditional BGP.
Yes.
So yeah, I have put out a question on the NANOG list, and I was hoping to get some answers if there are measurements out there regarding traditional BGP convergence.
Well, I'm thinking more in terms of the context of your simulation. Running a normal, say, zebra or a bird or something like that, feeding it the same routes, measure it, then run zebra or bird plus your BGP sec stuff, feed it the exact same routes, and determine what the difference in time is. That's what you're missing is basically your control data here.
Do you want to take?
Yeah, let Mehmet want
Yeah,
to say.
so that's a pretty good point. It's actually not as trivial of a measurement. So as you know, there are two reference implementations, one based on BERT, one based on Quagga. And we spent a lot of time trying to profile Quagga, but Quagga also works in mysterious ways. So it does stuff, stops, does it again. And we think about optimizations, right? So a lot of the operations in here sometimes depend on what you're using, whether it's Quagga, BERT, or some vendor's application. That's why we mention asynchronous operations. A lot of the times these particular operations can actually be hidden either on another core or while Quagga is doing something else. So the true goal that we have actually is as we profile these more, I mean, as you're right, this was the first step, right? How bad is it? And now, can we actually put it into these particular, routing engine software, but do it in such a way so you're not really seeing a difference? I don't think we're there yet, and that's probably the next level of research. But given the numbers, the 5-second numbers and this and that, I don't believe, for the next X years, as Shriram was mentioning, that convergence is going to be a problem. I mean, this may be adding a few seconds. Now, having said that, I do agree with you, a full analysis needed, and that's probably our next steps in the next 6 months or so.
Yeah, I think what I'm really looking for here is straight apples to apples comparison.
Yeah.
I understand that there are limitations around all the tooling that you're potentially using, and
Right.
it may not be as well optimized as one other implementation or whatever, but as long as you're doing the exact same thing in both cases,
Right.
this gives you a good comparison point.
Yeah.
Thank
If
you.
our router vendors are willing to work with Mehmet, for example, his optimizations for the crypto part can be included together with the router's BGP software, and those measurements can be done on real routers. So we're looking for some collaborations on that. Thank you.
Rüdiger von Deutsche Telekom. Essentially, on your last remark, Shriram, question, the optimizations that you have used here are not protected under any IPR.
Okay.
You want to speak to that?
All right. So there are multiple implementations, first of all. So as you know, we worked with NIST to implement this particular solution. So NIST actually has a framework where you can plug in multiple libraries, and that was with the thinking that vendors could actually have preferred libraries, or in some countries certain algorithms may not be available. In this particular case, I think P256 is available. So there's an OpenSSL implementation that will actually do all the BGP sec stuff, and you will be able to actually run this. So if your goal was to take it and do analysis and so forth, that's truly doable. Now the core crypto engine that we use, TaraCrypt, is actually a licensable product, and feel free to talk to us afterwards. But it's actually based on And again, you can have the BGP sec with all of these things to play with. If your optimizations you're after, then yes, we can talk about it.
Yeah, well, okay, kind of the comment I wanted to place first was, Sriram, I think you made the remark that, we are expecting hardware update will be needed anyway. I kind of would like to view work of this kind like we know the need for actual implementations in real field deployment are a couple of years out. And the interesting question is, what are essentially the requirements in processing power that we have to factor in planning our next generation of devices? Kind of hardware upgrades are necessary all the time. Yes, it usually doesn't happen every 6 months.
Right, right. So I should have mentioned what we are, the processor on which these measurements were done was a Xeon, Intel Xeon 3.5 gigahertz, single core, not, although we have numbers for multiple core. And with that, if that, what was state of the art general purpose processor a year ago, if that can be in the network, in the route processor 5 years from now, and if that is when you start seeing this 20% kind of adoption that we showed, then you are good 5 years from now. Even with last year's processor, you are good, right?
Yeah, well, okay, kind of. I want to be able to model what I have to expect, and kind of guess the margins of safety of my equipment planning.
Yeah, right.
And yes, for that it is really nice to have results that tell me yesterday's products will still work in a week or 2 weeks or 3 years. On the other hand, kind of doing the overall modeling, kind of getting the factors of how much additional power compared to what we have at the moment will be needed. Whether that's going to be faster processors or more cores or whatever.
Right.
Of course, the results about, well, okay, certain performance is needed single-threaded rather than multi-threaded, of course, is also an important dimension.
Right. Yeah, we can definitely help you with that. Or anyone else who's interested in that analysis, we can sit down and do it.
Yeah, I'm sorry, folks. We're running a couple minutes over. I wasn't good about closing the mics early. So if you got a quick one, why don't you bring a quick one? But otherwise, we might have to invite you to maybe have some Q&A outside if you're available.
So Phil Rosenthal, Beluga CDN, and if it's too long to answer, it might just be something for you to think about. But when you add security into something, you also need to think about, is that security perhaps introducing a new problem? What about the risk of denial of service attacks? You know, so this would be a very special case, but say a nation state who meant to attack another nation state might set up bogus clients all around the country, build AS path lengths of 10 or 50 ASs, all with BGP sec. How many updates per second does it take to completely take a network down? And does that then end up requiring countermeasures like scheduling or or caching or whatever to prevent that as an attack method?
Yeah. Thank you for raising the question. The drafts and the RFCs have always a security section where we did discuss all the security problems that may arise as a result of BGP sec implementation. So that's discussed in fairly good detail in the BGP sec draft. Let me refer you to that, and also we'll be happy to chat since we are running out of time, we'll be happy to chat one-on-one with you about your
There is actually an
more
implementation in place, so if you want to talk to us, I can describe it.
All right, thank you.
Thank you, sir.
Thank you.